Hi, you guys. So today I have with me problem 7.5 from Young and Freedman's University Physics textbook. And so I absolutely love energy conservation problems. Freudian slip there, but energy, I'm gonna mix this up this whole video, so just excuse me in advance. But energy conservation problems, because they're actually like so fun and easy once you get the hang of them, and you'll just really enjoy them. Trust me, like once you really understand and practice, it's so much fun to do. These were my favorite problems in high school and undergrad. Okay. I'm such a nerd. Okay, so before we get started on this, please don't forget to like and subscribe and share. Yes. Okay, so actually one thing that I wanted to bring up about this problem is that there's actually two ways to go about this. So one is from an energy perspective, like an energy method, and the other is you can actually solve this question using kinematics. So what I'm thinking to do is that I'm going to upload this video hopefully twice. Don't like I'm gonna try. So I don't promise, but I'm gonna upload this video obviously right now if you're watching it, it's uploaded using the energy way, and then I'm gonna do it again using the kinematics way. And you'll see like how cool this way is because it's so much easier. But also I'll get into like what restrictions there are and like when you can even actually use this because you can't always use energy to solve like kinematics problems, but mostly you can. And that's what's so cool, that it's so awesome. Okay. Anyways, so a baseball is thrown from the roof of a 22.0 meter tall building with an initial velocity of magnitude 12.0 meters per second and directed at an angle of 53.1 degrees above the horizontal. What is the speed of the ball just before it strikes the ground? Use energy methods and ignore air resistance. B, what is the answer for part A? If the initial velocity is at an angle of 53.1 degrees below the horizontal, if the effects of air resistance are included, will part A or B give the higher speed? Love this question. So much learning, so much problem solving, and so much thinking. And I think that's what makes this problem so great because we're just going to cover a lot of material in this video, hopefully. Okay, so in this problem, I know that like I said in my last video with like the energy, yeah, the energy video that I did before this, that you don't usually need to draw a diagram. This is actually one of the exceptions. So because we have such a detailed kinematics problem, you're going to use your physics intuition once you develop one, but or yeah, like once you develop your physics intuition, that's what you're going to use. But as of right now, I'm assuming that if you're a beginner, this is sort of all new to you. And so we are going to draw a diagram for this, and just because, yeah, it's so similar to our kinematics problems. Okay, so let's go ahead and do that. So over here, I have a building. Oh, I don't like how I started off with that speck of dust. Okay. And just for funsies, I'm going to give this like a bunch of windows just because I think it's kind of cute. It'll make for a good thumbnail. Okay. And so we have a person who's going to be at the top of this building, right? And you know what? I'm just going to go a little bit more into detail, like step by step, using information from the question to draw the problem. So, okay, let's start again. So a baseball is thrown from the roof of a 22.0 meter tall building. So this person is on the roof of a 22 meter tall building. That was like so gross. So I'm going to rewrite that. Okay, 22.0 meters. Okay, so now this person is on the roof and they're throwing a baseball. Now I know baseballs are red and white, but that's going to be so hard to draw. So I'm just going to draw this red ball and we're going to pretend it's a baseball. And it sounds like, so an initial velocity of magnitude 12.0, and it's directed at an angle above the horizontal. That means that it has an X and Y component. So this is a projectile motion problem. Again, so cool. Okay, I kind of like that. It's not the best projectile that I've drawn, but it'll do. And we're just going to go ahead and draw the ground because it says what's the speed of the ball right before it strikes the ground. So like what is the ground? Well, it's going to be the height that the building starts at. Okay, so I just want to make one thing clear because I feel like I might get questions on this. And it's that notice how this person, when you're holding a baseball and you're on top of a roof, right? So like let's say your building is 20 meters tall, 40 meters tall, 100 meters tall, on top of a skyscraper, doesn't really matter. Okay, you're probably thinking, well, I'm not at ground level, so this person is probably holding this ball at like, 1 meter above the ground. And yeah, that's true. But in this question, we're just going to sort of ignore that fact. We're going to pretend that the person is actually, oh my God, there's like a fly and it's going to fly into my tea. Just give me 1 second. Okay, just covered up my tea. Okay, so as I was saying, that there's this person holding a baseball, and you're probably thinking, well, it's probably like 1 meter above the ground. So shouldn't we use a 23-meter estimation? Well, yeah, like if this were to be really precise, that's exactly what you would do. But for the sake of this question, because we're not really given information on how high above the ground or how high above the ground of the roof that this person is holding the ball, we're not going to even like get into that just because this is a textbook problem, and we're going to just pretend that 22 meters is not only the height of the building, but it's also the distance from also the height of the ball to the ground. Okay, so maybe this person's like lying down and throwing it. It doesn't matter, but we're just gonna use 22.0 at face value, and we're not gonna do any like predictions or any adjustments from there. Okay, so part A is asking for what is the speed of the ball right before it strikes the ground. Okay, so something I'm going to bring up right now is that you might have noticed that I don't have a up and down, plus and minus like coordinate system type thing, right? So like I haven't defined what's up, what's down. I mean, well, obviously up is up and down is down, but like if up is positive and down is negative, or if up is negative and down is positive. And there's a reason for this. And that reason is that in energy problems, we don't actually set like G as minus 9.8. We don't do that. And the reason is because it's actually like intrinsically, so potential energy is actually like a derivation that comes from force that already has like the minus mg to it, right? It already has the minus g in it. And so because of that, we don't really use a minus sign for gravity when it comes to gravitational potential energy. Okay, so that's that. I just wanted to bring that up because that is usually like a point of confusion. And I talked a little bit about this in my last video as well. But you do look at up and down in terms of your reference point for height. What do I mean by that? So if your reference point is like this, right, and your H is this, H1 is this, or H2 is this, you are going to use plus and minus. Here, there will be a plus and minus, right? But there is no plus and minus for gravity when it comes to gravitational potential energy, okay? There is not there. Okay, so I hope that that's clear. And this is like from a problem solving perspective. I'm not going to get into like the details of why we don't have the minus here, because that's like an upper level physics derivation. So you're just going to have to trust me on this. And if not, you can just do some reading on your own. Or I guess maybe I could dig up some of my old notes from like second or third year, and I don't know. Probably not. I don't know where those notes are right now. Actually, I do. I like to do basic problems because they're fun and easy. Okay, so all right. Mm, let's write down our knowns now. Now that we've cleared up this U is equal to MGH business, right? So the H and the G. Oh, that was gross. That was so gross. That was a horrific arrow sign. A little bit better, but okay. So now let's write down all of our knowns. So our knowns are a baseball is thrown from a roof. And the height at which it's thrown is 22 meters. Okay. And that's above the ground. So we're assuming the ground is like the 0 level. Okay. So with an initial velocity of magnitude 12 meters per 12.0 meters per second and 53.1 degrees above horizontal. So just written it down like that. And what else do we know? We know that G is 9.8 meters per second squared. What else do we know? That seems to be it. That's what we know for this problem. Okay, so how are we actually going to solve this? So we're going to use energy. And what does that mean? Because we haven't done a problem like this. This is sort of brand new for this channel. And it's that we look at the ball, right? So let's say that this ball at point 1, right? So this 1 and this 2 that I've drawn here, we're going to assess what energy it has at state 1 and at state 2. And because it says ignore air resistance, and this is just like, this indicates to us that we can actually even use an energy method. Because if there is air resistance, then energy is dissipated. If there's friction, then energy is dissipated. If there's air resistance, energy is dissipated. And when energy is dissipated, you can't use this method. So that's like the caveat. I think I used that word right. Okay, so like that's the caveat when you use energy methods, right? You have to make sure that you're not, that it's that energy is conserved. And that's what energy conservation means, that at point 1, the energy is the same at point 2. So let's write that down just for our own knowledge. So energy at 1 is equal to energy at 2, right? So at 1 is equal to energy at 2. And that, right, this means energy is conserved. And I have another really fun problem we're going to do where energy is not conserved and how we know how much energy is like lost or dissipated. Energy is never really lost. It's just converted from like one form to another. So that's why we say like dissipated. But okay, so energy is conserved in this problem, in this scenario. So, okay, if it's conserved, what are the energies that are like what forms of energy, not energies. So what forms of energy are available or are present at point 1 and what energy types are present at point 2. So at 1, we're at a certain height, which means gravitational potential energy. So it's going to be mgh1, right? And it's leaving at some sort of speed. So that means that there's also kinetic energy. And what about, is there anything else? I can't think of anything, so no. But like other forms would probably be like elastic potential energy. There's another one I can't think of right now, but I feel like there's probably more as well. I mean, yeah, but for this problem, all we really have here is gravitational potential energy and kinetic energy, right? So we have that at point 2 or point 1. Now, what about at point 2? So at point 2, we only have kinetic energy because remember, we're on the ground. So H2 is 0, 0. So all we have is kinetic energy. And remember how I said energy is never really destroyed, it's just converted from one form to another, especially in this situation when we're ignoring air resistance because we're assuming in this problem, like, technically there is no air resistance when they say not technically. That's wrong. So In this problem, there is no air resistance. Yes, so in this problem, because we're ignoring air resistance, we're assuming that there is no air resistance. And that means that all of the energy that was, all the energy that is in MgH1 is converted to, so all the potential energy is actually converted to kinetic energy, right? Because we have no kinetic energy in at point 2. Does that make sense? Also, sorry, I'm recording this like really late at night and I'm just forgetting how to speak. Okay, so I hope that makes sense. At point 1, we have gravitational potential energy and kinetic energy. And then at point 2, we just have kinetic energy. And the reason that we don't have gravitational potential energy at point 2 is because we're at height 0. And that means that there's no gravitational potential energy there. Okay, and all the gravitational potential energy that is in part 1 is actually converted to kinetic energy. Okay, so now let's go back to this right over here, this point. Energy at 1 is equal to energy at 2. So if we want to find out what the energy at 2 is, or I'm going to highlight it, is at V2. Oh, I don't like that. Okay. So if we want to find out what the energy is at V2, we need to isolate for V2. And how do we do that? How do we even come up with an equation? Well, like this. Or no, not green. Let's do brown. I feel like that'll be helpful. Okay. Well, we know that, energy at 1 is mgh1 plus half of mv1 squared. And that's equal to half of mv2 squared. Okay, so that's all the energy at 1, right? And this is all the energy at 2. And because energy is conserved throughout the process of this ball going from, point 1 to point 2, that means that, again, these energies on both sides are, the energy on both sides are equal to each other. I don't know why I'm calling it energies, because I think in my head I call it that. Okay, it doesn't matter, I'm so tired. Okay, so okay, next we said we're going to isolate for V2. So let's do that. So mgh1 plus half of mv1 squared. Okay, we're going to multiply both sides by 2, right? So then we get rid of that half. So we're left with mv2 squared. And now we're going to divide both sides by m. And then we're just left with v2, right? v2 squared. So then we're going to square root both sides. And that means that v2 is equal to 2 mgh1 plus mv1 squared over m. Now, I did something really stupid, but I'm just going to bring it up now. The first thing I should have noticed is that these m's actually all cancel each other out. And that's actually sort of a trick. When you have an energy problem and you don't get the mass, then it's probably just going to cancel out. Okay. And so for here, we can see the same thing, that m and all the m's cancel out. And so really V2 is 2 gh1 plus v1 squared. And we're going to square root that. And yep, that is consistent with what I got in my notes, although I went about it a little bit differently, but ultimately, yes, got the same answer. Okay, so now all we have to do is plug in our values, and then we have our answer for V2. So what is that? V2 is equal to 9.8 times what's H1? It's 22 meters. And then what's V1? V1 is 12 squared, right? Well, V1 is 12, and then V1 squared is 12 squared. Okay. So what is V2? Let's plug it into our calculator. And that is 2 times 9.8. Actually, I just want to double check something. Did I make a mistake? I think I made a mistake somewhere here. Oh, I got it. So sorry. Over here, notice how, yes, we distribute the 2 into here, but we also distribute it right over here. So really, this should be 2 times mgh1 plus mv1 squared, right? And this over here should just be that. And yeah, this should be that. Does that make sense? Because one thing that I just forgot to do is that, yeah, when I distributed this, I added an extra bracket in there. So, okay. Now that should make sense. But yeah, I'm not going to go into details just because this is algebra, and I'm sure you know that because you guys are always catching my mistakes. So, which I really appreciate, by the way. Thank you. But that should be helpful. I hope that's helpful. Okay. So now we're going to plug this into our calculator. And that's why I always plug things into my calculator like on screen because, or in the video, because yeah, whenever I don't do that, I end up making like a mistake because, you know, I forget to distribute something or I miss a bracket or misplace a bracket or a plus and a minus sign. And then just my entire answer is like, the process is right, but there's like more mistakes. Okay, I'm talking way too much. So 9.8 times 2 times 22 plus 144, square root that, and I'm getting 23.98 meters per second. That is our V2. Okay, 23.98 meters per second. So that's our V2. I'm just going to go ahead and down to 53.1 degrees. Okay, because that's above horizontal. Perfect. So that's our answer for part A. Now part B, part B, what is the answer for part A if the initial velocity is at an angle of 53.1 degrees below the horizontal? Excellent question. And you're about to see the beauty of using energy methods, right? You're about to see how much sense this makes. But before I actually go ahead and do that, I wanted to bring up, just tie this a little bit into kinematics, right? Because I did talk a little bit about that, so it's only fair to tie it in again. So notice how much easier it was to get V2, right? If it were kinematics, as you'll probably see in another video that I'll make with this exact same problem, first you have to solve in the y direction and then in the x direction, and then you have to use Pythagorean's theorem, and then you get your V2, right? Because you have to Pythagorean theorem the x and y. And yes, I know Pythagorean theorem is not a verb. I'm too tired to think about that right now. But ultimately, you guys probably have like a lot of experience. At this point in the course, you have a lot of experience with projectile motion, and you know that when you approach it that way, it just takes so much work, so much more writing, so much more thinking, and this way is so much easier. And I hope you see that. Or at the very least, I hope you'll see that with a little bit more practice. Okay, so now part B. What is the answer for part A if the initial velocity is at an angle 53.1 below the horizontal? So let's look at how that would look like. So I'm going to use like, let's use, I'm going to use a color that complements this, but okay, we'll just use dark blue. Okay. So let's say that this is 53 degrees below, 53.1. So 53.1 degrees below. And it's probably going to be like some sort of path like that. Like this is curved and this is, yeah, this is also a projectile, but it's 53.1 degrees below. Okay. And maybe I'll just do this so that it's like a little bit more curved. I'll try to erase this. Just do it again, actually. Okay. Okay. Okay, yeah, I hope that's a little bit more clear now. But this is the problem. Or sorry, this is the setup for part B. 53.1 degrees below the horizontal axis. Now, I want you to think, what's the answer going to be? The answer is identical, right? And how can I say that right off the bat? Like, how can I say that without even doing anything? Well, look at part A. Did we use this 53.1 degree angle anywhere? Do you see that anywhere in part A? And no, we didn't. And so that means that if we don't need it for part A, then we don't need it for part B, then aren't those both the same answer? And the answer is yes. They are exactly the same answer. It doesn't matter if it is above the horizontal or below the horizontal. When there is no air resistance, they are going to have the same final speed, which begs the question, part C. If the effects of air resistance are included, will part A or B give the higher speed? Okay, think about this now. So, what is air resistance? Air resistance is almost this type of friction, right? And so if we have a longer path, we're going to experience more air resistance. And we're going to be slowed down more because we're in the air for longer. And if we have a shorter path, we're going to encounter less air resistance. And that means that we're going to be slowed down less, which means that when we are including air resistance, part B will have the higher final speed because it travels a smaller distance than path A, or it has a smaller path than part A. I hope that makes sense. And I'm just going to write that down just for like completion, I guess. So let's write it down over here. So what color should we use? Let's actually use dark green because we just replace that. So B, they're the same. Oh, that was the weirdest T ever. They're the same. Okay, and then C, if the effects of air resistance are included, part B will give the higher speed. And why? Well, we said that more like larger path means larger air resistance. And that is going to lead to slower final speed. And then the reverse is true. Smaller path means less air resistance, means higher final speed. Okay, so that was this problem. I know it's a really long video, but there's a lot of content. I think, in my opinion, there's a lot of learning. So I really hope you learned something. And as per usual, if you have any questions, comments, concerns, please feel free to leave them in the comments or send me an email. And thank you so much for watching. Please don't forget to like and subscribe and share with your classmates, friends, whoever you like to do physics with. And see you next time. Thank you so much for watching.